For this section, we're going to be talking about spectra, and spectra are basically rainbows. You take a beam of light and you pass it through a prism or a diffraction grating, and when it goes through the prism or diffraction grating, it breaks apart to the light according to the colors. So you might think of rainbow, I'll call it a spectrum. So technically it's just a beam of light separated by color or energy or wavelength or frequency. We are only going to look at visible spectra, so the colors of the rainbow, but there are also spectras that you can study in the infrared and the ultraviolet, right? All the different colors, bands of light. Oftentimes, if you look through a diffraction grating or prism, you'll see the spectra. It'll look like a rainbow if all the colors are present. But that can be hard to record and share and discuss, so a lot of times we'll just turn it into a graph. And so we'll graph it out, and we might, here let's label it simply from red to violet. So this axis down here, the horizontal axis, is just the color or the energy of the light that you're talking about, and then how high it is tells you whether or not there's light at that color. So there is violet, so this is going to be up here a bit. There is red, so this curve is going to be up here. And according to this graph, it's brightest in about the orange. So it's also good to graph it out this way because the human eye is most sensitive to red, green, and blue. We're not very sensitive to orange or purple or yellow. So you can actually see what's going on in this graph. Let's pretend that there was no yellow. So imagine this area right here was instead completely black. There's an absence of light here. There was none of the yellow light coming through in that beam. It's all black. Then the spectra would look the same. There'd be light at the green, light at the blue, but then when you hit yellow, the graph would drop down and there'd be zero yellow light, and then it would pop back up and continue on. There are 3 categories of spectra. When things get complicated, you can mix and match them a little bit, but for us, let's just keep it simple. 3 categories. The first category that we're talking about is continuous spectrum. Right, so continuous spectra. This is a category. A continuous spectra basically means that if you were to look at it with your eye, you would see a full spread of colors, all the way from red to violet. Okay, full rainbow. That's what continuous spectrum means. When that is made out in space, it's because of 2 things. You have something dense, and that dense object is warm enough or hot enough to glow visible light. So you need something dense, and it has to be hot enough to glow. Right? When you have those 2 things, it should make a continuous spectra of light to give off all the colors. An incandescent light bulb, right, we have an incandescent light bulb right here in this figure. Right? The incandescent light bulb glows because the metal filament, that tiny little metal filament, is dense, and it gets hot when you pass electricity through it, and that makes it glow. So if you had a diffraction grating, which I usually pass out in my seated classes, and they can look through them, you can see a full rainbow. Right. The second type of spectral category is called an emission spectra, and it looks different to your eye. Right. Emission spectra. If you were going to look at some light coming from an object, you would notice that there would be no light coming in at most of the colors. Here it shows it as black, but that just means absence of light. So you would see a bright orange line in this case, a bright yellow line, two bright green lines, a bright blue, two bright purples, but you would see nothing in between them. All right? So bright spectral lines would be an emission spectrum. And you get an emission spectra when you are looking at something out in space, such as a cloud of gas that is not dense, or a nebula. Not dense, so you might be able to see through it. Right. And that cloud of gas that's not very dense needs to be warm enough or hot enough to glow in the visible light. So if you have a bit of gas and you heat it up, and the light is going to come from that cloud, come from that sample of gas, it will give off only very specific colors of light. And that would be your emission spectrum. Those colors of light are very special. So the fact that you got an orange and a yellow and two green, that's very, very special, because every element, every molecule, every isotope has its own unique set of colored lines. So it's like a chemical fingerprint. Right? So whatever this composition of this gas is over here on the left, its composition depends what lines you will see. So we can use that backwards. We figure out what lines you see, and that lets you figure out the composition of the gas. So let's go into that a little bit more. So in the center of each atom, you've got the nucleus. So here's the nucleus of hydrogen, the nucleus of helium, the nucleus of boron. And that's where all your protons and neutrons are. And what's in the nucleus affects the electron energy levels. So you've got energy level 1, energy level 2, energy level 3. But notice hydrogen's spacings are different from helium. Helium's spacings are different from boron. And that's what gives you the unique sets of colored lines for each element, for each molecule. So electrons, when they jump from 1 to 2 or 2 to 1, they're going to either absorb or emit light. That's what this figure is over here on the right. If an electron was on energy level 3 here, that's higher up in energy. So when the electron drops from 3 to 2, the electron lost energy, and the energy has to go somewhere, so it goes into light. So when electrons drop down in energy, they give off light. And that's the emission spectra. That's an electron dropping down. That's an electron dropping down, giving off light. Right. So let's pretend here that, how about boron? Let's use boron. Let's say an electron drops from 4 down to level 2. Right? And let's say when that happens, it's going to give off red light. Right? The 4 to 2 transition is specifically going to give off red light. Right? The 5 to 2, if there was an electron going from 5 to 2, that's a larger gap in energy. So when it gives off a piece of light, a photon, a wave of light, that wave of light is going to have more energy. So it's not going to appear red to us, it would appear something higher energy, like maybe yellow. And we can do one more. What if the electron was at level 6 and it's going to drop down all the way to level 1? If an electron were to jump from 6 to 1, it would give off a piece of light with even more energy, because this jump here is even bigger, so it might give off blue or violet light, or maybe even ultraviolet. Okay. So each energy transition, 6 to 1, 2 to 1, each time an electron jumps, it gives off one very specific color. So each atom, if we're looking at this animation, each one of these dots would be an atom. White dots are atoms. Each atom can only give off one photon of light at a time. Maybe blue, maybe red. But in a cloud of gas out in space, there's billions of atoms just in one cloud. So as a human looking at the whole cloud, you can see all possible spectral colors at once. Some atom is going to be giving off the purple, and while that's happening, another atom will give off the red, so you can see them at the same time. To give you an example here of the unique spectras, this is hydrogen spectra. It's the only one I have memorized. It has a red line, a bright teal line, a blue line, and it actually has two purples. It doesn't show the second one here. That's the only one I have memorized. But if you were to look at the spectrum of helium, it would be unique and different. If you were to look at the spectrum of lithium, unique and different. Carbon, sodium, neon. So when we look at a nebula out in space, it's not just going to have pure hydrogen atoms. It's going to have a little bit of lots of stuff. So maybe the spectra we're going to see from space is going to have all of those elements in it, all giving off their lines. So it's going to look pretty messy. And it is people's jobs, and now computers do a lot of the work, to go through and figure out exactly which lines are in there, which means exactly which elements are in there. And they go through and figure out, oh, I see the lines for hydrogen. Let's take a count of those and figure out what's left. Ooh, I found the lines for helium. Let's take those out of the light and see what I have left. One by one by one, figuring out what's in there and trying to figure out all the elements. It's more complicated than that even, because if there was a lot of lithium, lithium's lines would be brighter, so you could actually figure out the amounts of all of them. So it can be tedious, but it's very worthwhile. You've never been to a nebula, but you can figure out what it's made of. How much hydrogen to how much lithium. It's really worthwhile. The last category of spectra is called an absorption spectra. An absorption spectra is basically the two categories put together that we've already talked about. So we're going to have a background light source, and in this case we're going to have a dense and hot, dense and warm background light source. So that's going to be giving off the full rainbow. It's going to be giving off the full rainbow, all the colors, continuous spectrum. That light, before it gets to us, is going to go through a nebula or an atmosphere or something, some cloud of gas. And that cloud of gas is going to be not dense, so not metal, but maybe an atmosphere like air. And it has to be cooler than the background. So imagine a background star and the starlight's trying to get through a nebula. And by the time that beam of light gets to us and we pass it through diffraction grating, this is what it would look like. A background rainbow with the spectral lines missing. A background rainbow with the spectral lines missing. Okay. Right. So here's an animation of that. Here's our background star. It's got a hot, dense core. It's going to be giving off every color of the rainbow. So there's all the photons, all the little pieces of light going to your telescope. It says white light from star because a human, if you see all the colors of the rainbow coming into your eye at once, your brain says it's white. Right? So that's every color. You can see that down here on the spectrum. Every color peaking mostly in the greenish blue. if there were a nebula, a gas cloud, or an atmosphere in between us and the star, that gas cloud would only interact with the colors that it's allowed to. Remember the electron levels? That cloud of gas can only interact with light that has the perfect energy to move the electrons from level 2 up to 5 or 1 up to 4. So this nebula is going to interact with only the colors that that gas can interact with. In this case it's hydrogen, a red, a teal, a blue, a purple. And all the colors of light that hydrogen cannot interact with, it just keeps going through the cloud. Remember, it's not dense by definition. Light can go through it. So you see all the colors that can make it through the nebula, but the cloud will scatter or absorb the colors that it's allowed to, the red, the teal, the blue. So by the time it makes it to your telescope, you don't see them. They've gone missing. That's an absorption spectra. Going back here a second, all stars show absorption spectras. All stars, because it's the core of the sun. The core of the sun is dense and hot. The core of the sun gives off the background rainbow. But before the light can get away from the sun and get out into space and get to us to see it, it has to go through the sun's atmosphere. And so all stars have atmospheres, and the star's atmosphere will take out very specific colors. Okay. Then that starlight has to go through Earth's atmosphere. Earth's atmosphere will take out a few more. So spectra can get complicated fast. We're going to keep it simple. Okay. We're going to now talk about thermal radiation. Okay. But basically what we're doing is going back to the full rainbow, the continuous spectra, and look at it a little bit more and see what it can teach us. We've already found that the spectral lines can tell us about the composition of the nebula. Right? So the spectral lines tell us about the nebula, but the rainbow is going to be able to tell us about that hot, dense light source. So let's find out what we can learn from it. So I consider myself warm. All the things in my room are warm. So everything in here is glowing in infrared light. Your desk is glowing in the infrared light, you're glowing in the infrared light. If you heat up an object, especially metal is nice and easy, you heat up an object, it'll start to glow in the visible light. It's also going to be giving off more infrared light, but now also visible. Heat it up even more, it'll get brighter and it'll change color. Heat it up even more, brighter and whiter. It's not very typical in everyday life, but if you were to be able to heat it up to say 30,000 degrees Fahrenheit, that piece of metal would start to glow blue. It'd be even brighter and it would start to glow blue. So the idea is that a hot, dense object will glow, and what colors and how bright it is only depends on its temperature. So that's thermal radiation. Thermal radiation is basically just that the spectra, how much red, how much yellow, how much green, only depends on the temperature. And this only works for hot, dense objects. Hot, dense objects. It's not going to work for a nebula. It's not going to work for an atmosphere. It needs to be the core of a star. It needs to be the metal in a filament of a light bulb. Right. Hot, dense objects. Only depends on the temperature. So let me use my temperature slider here and say for human, This is what our spectra looks like. Probably even further down. There you go. For human, we only glow in the infrared. But if you were to get something hotter, like a fire poker, right there, it just starts to glow, just a little bit of visible light, and it's all in the red part of the rainbow. So it's going to glow red. Heat it up, heat it up, heat it up, it'll grow brighter, and you can tell it's getting brighter because the curve is getting higher, and there's going to be some extra colors in there. This would still appear red to your human eye. Right, the red, the yellow, the green, the blue, it's all going to merge together and it's going to look reddish to your human eye. Heat it up. Whoops. It's going to start looking whiter and whiter. At this specific temperature, it would glow white because there's pretty much equal amounts of red, yellow, green, blue. They're all pretty equal amounts. It's going to be pretty bright. The curve is pretty high. But things can glow bluish if it's even hotter. Hot, dense objects can glow bluish. So that's the bluish right here, is it's a little bit more blue. But if you look up at the sky, at the stars at night, you won't ever see a just pure blue star. It's going to be whitish blue. The whitish blue is because there's still lots of red, lots of yellow, lots of green. And so all of those will merge into the white, and then on top of the white you have a little bit more blue. Our star has a surface temperature of 5,800 degrees Kelvin, right about there. That's the thermal radiation spectrum of our sun. The most prominent color in our sun spectrum is actually green. Our sun mostly gives off green light. It peaks right at the green. If you were in space looking at our sun though, which is not advisable, it would hurt your eyes, it would look white because there's pretty much equal amounts of all the colors. So our sun would look white to us. Why does it look yellow on Earth? White light is all the colors of the rainbow, and our sun would look white. But as it tries to get through the atmosphere, the blue light is scattered out to make the sky blue over other people. All right, the blue light that you see coming from the sun gets scattered out, so what you see coming down from the sun is every other color of the rainbow: red, orange, yellow, green. And when your brain sees red, orange, yellow, green coming into your eye, it says yellow. So our sun looks yellow because the sky is blue. But if you were in space, it should look white. Still talking about thermal radiation. Here's two example curves of thermal radiation spectra, or it depends only on the temperature. 5,000 degrees Kelvin. It's about a little bit cooler than our sun. 7,000 degrees Kelvin. Much hotter than our sun. Right, so for the cooler star, can you see that it peaks in the red? Reddish orange? Your eye would merge all of this together and say, oh look, I'm looking at a reddish star. It's got a little bit of a red tint to it. You would look at this star and your eye would merge all these colors together and you'd say whitish blue. For thermal radiation, we've got two laws. You don't have to have them memorized, but you should know what they mean. Right? The first law is a hotter object emits more light at every wavelength, so at every color, per unit area. Right? So a hotter object emits more light at every wavelength, or at every color, per unit area. So look at the two graphs. Does the hot star emit more infrared than the cool star? True? Does the hotter star emit more red light than the cool star? True. Does the hot star emit more blue light? Yes. And the hot star also emits more infrared light. So there's two things I would mention about this. First, this basically means that a hotter star tends to be brighter per unit area. Hotter stars are brighter. Right? Second thing I would mention is that what this means is that a blue star emits more red light than a red star, which is a little bit counterintuitive. The blue star, the hotter star, emits more red light than the cooler red star. Second law, hotter objects emit light with higher average energy. And one way we gauge the average energy is also by looking for the peak of the graph. So up here, the peak of the graph, the maximum wavelength, the maximum color. Here's the peak here. What this basically says is that as you heat up the star, as you heat up your object, that peak color will shift towards the blue, towards the higher energy. So a cooler star here, its brightest color will be in the lower energy, red. And as you heat it up, that maximum color, your average energy of your light is shifting towards the blue or towards the ultraviolet. So what this one means is that hotter stars look bluer. Hotter stars look brighter. Hotter stars look bluer. Alright, so any spectrum that has spectral lines, we can tell the composition of the nebula. So there were two of them with spectral lines, remember? The absorption spectrum and the emission spectrum. Both of those had lines, and we could find the composition of the gas. This, now, studying the rainbow, the background rainbow, lets us tell the temperature of that hot, dense part. So there's two categories of spectra that have rainbows. Right? The continuous and the absorption. So for both of those categories of spectra, we can find the temperature of the hot, dense object. Because we need to look at light as much as we can, there's one more thing we can learn from light. And basically, by looking at the spectra, we can actually find the speed of a star. Right. So in this image, there was an object, and it was located at S1 here, source 1, and it gave off a wave of light, and that wave of light moves out with time, so that's why it's all the way out here. It's had time to get further away. But by the second time, it's moved. That light bulb has moved, that star has moved, and it gives off a new light wave, but it hasn't had as much time to travel outward, so it's only here, and 3 and 4. Right? So all of these waves of light are no longer concentric, they're skewed off to the side because the object is moving. So, if your light source is moving, in this case towards this person, that means what that person would see is that the light waves appear bunched up. The light waves appear more bunched up. So what might have been a yellow wave or a yellow light coming out of the light bulb here would not look yellow to this person anymore. It would look green or blue or ultraviolet. Something higher energy, anything higher energy, depending on the speed. Right? For this person back here, the light waves would appear to be stretched out, just because the object is moving between the pulses of light coming out from it. Right? The wavelengths are spread out. So what might have been a yellow light coming from that source, the yellow light is going to be stretched out by the time he sees it. So it might not look yellow anymore. It's going to be stretched out. Maybe orange, maybe red, maybe infrared. So if the light source is moving towards you, it's going to appear too high energy. We call that a blue shift. It means shifted to the higher energy. If the light source is moving away from you, we call that a red shift. Right? The light has shifted to a lower energy. Okay. You have to be careful, because what if a blue light, let's say we have a blue LED light bulb, and we have it moving towards a detector, moving towards a camera, moving towards a person really fast. The blue light can be blue shifted, which means to the higher energy. So the person who's observing a blue light bulb coming at them might see purple, I should say violet, or ultraviolet. Right? Blue shifted does not mean it appears blue. It means shifted higher energy than it should have been. Red shift does not mean seeing red. It means shifted to a lower energy than it should have been. The amount of shift tells us the speed. So by looking at spectras, we can tell the speed of the object. Fun bumper sticker that I've seen. There's a bumper sticker that says, if you drive fast enough at a red light, it will appear green. And that's true. It's just the speed that you would need for that to be true is a fraction of the speed of light. So it's not going to happen for us driving at stoplights. So we use the Doppler shift to find the speed of objects. One thing we do with that is look at binary stars. So in this animation, we've got two stars, A and B. We are actually not even looking at star A, we're only looking at the blue star. So the spectrum of the blue star is shown below. And notice Earth here is off to the left. So if star B moves towards us right now, all of the spectral lines should shift towards the left. When star B is moving away from us right about now, all of the spectral lines are shifted to the right. All of them are shifted to the higher energy, and then all of them are shifted to the lower energy. That lets us find the speed right when it's coming towards us, and it lets us find the speed right when it's going away from us. The Doppler effect cannot tell us anything at all about the speed if it's moving across our line of sight. So when it's right here, it's moving across our line of sight, the Doppler shift doesn't do anything. And when it's right here, moving tangential to our line of sight, we can't use that information at all. It's only towards or away. Right. This purple line almost blue shifts into the ultraviolet, which is possible. Visible lines can shift to invisible parts of the spectrum. Did you notice that the spectral lines are shifting, but the rainbow appears not to move? The rainbow is moving as well, but when the rainbow moves, let's say it's shifting all the way towards the purple end, You don't get a blank spot in the red because there was more infrared that can shift visible to fill it in. So the rainbow doesn't appear to move, but it is. And so when we're looking for the Doppler shift, we look at the spectral lines because we know exactly what wavelength those lines were supposed to be at. And so we can tell the exact amount of shift to where we see the line and get the speed. Right. So that section has a lot of material. It has a huge amount of material. I would say spend some time on it, but also make sure that you go back and forth to it a couple different times. See it, refresh it, study it at least 3-4 times before the next test.